Hello, everyone, and welcome to the first episode of Honest Discussions. I'm your host, Dr. Randon Patterson, and Honest Discussions is just that. It is a platform that is dedicated to having uncensored conversations with the scientists that are actually doing the research that are shaping the modern world. Much of what we hear in the media and on the news comes from a small handful of scientists that actively cultivate a media presence. This is not that. These are the people that are actually in the trenches doing the research. And we're going to be speaking to people across all areas of science, from astrophysics to biology to medicine to consciousness, you name it. If it's kind of interesting, we're probably going to talk to somebody that does that. And today, my guest is Dr. Geriant Lewis, who's an astrophysicist from the Institute of Astrophysics in Sydney, Australia. I had a really delightful conversation with him. His new work is exploring how time dilation of quasars may provide us a watch that can tell us how old the universe is and many other things. Geriant is also an amazing physics historian, and I learned a ton from talking to him. Even though we don't agree on everything, it was really enjoyable to speak to someone who has such a deep knowledge about physics historically and has a really broad-based general science background. So it was really fun to talk to him. If you like the show, please like, subscribe, and share with as many people as you can. This platform is dedicated not only to improving the dissemination of science to the public. I really want this platform to be a mechanism for providing research funds to all areas of science. And the first step towards those goals is getting the channel monetized. So the faster we can get to 1,000 subscriptions, the faster this is going to happen. Your support is required to achieve these goals. In the words of Rage Against the Machine, it's time to take the power back. And the one way we can take the power back is by renewing the connection of society.
Yeah, absolutely. Well, something happened. I mean, post World War II, I think there was a big appreciation of the role of science in society, but it somewhat is dwindled, and people seem to forget that the latest device, the mobile phone, etc., which you can't see there, but this is all the result of scientific inquiry, right? It eventually becomes into the realm of engineering, but it starts off with scientists asking questions. And that part of the story, just I said, seems to be lost. And I think it's for a number of reasons, from all the way from the top, from the messages from governments down to the portrayal of scientists on TV.
I couldn't agree more. In reality, the basic science has been lost. I mean, in our country, we have senators that go up and say, they're studying old people playing video games. What a waste of our tax money. And it's like, no, that is anything but a waste of our tax money. Understanding the neurocognitive improvements that may occur, which have been ancillarily implicated in keeping people's minds healthy to this point. No, they're actually studying it, figuring out, can you develop games that actually improve mental cognition later into life by 20, 30, 50%? If you can, that is one of the cheapest medicines and healthiest medicines that's ever been developed.
Absolutely.
But that's,
yeah.
and but that's basic science. And I used to say this to my students all the time. Basic science is where the real understanding comes from. And I feel like what's happening right now is a lot of pillars of technology and creation that we've built are on pretty shaky fundamentals, because we're too quick to race to this is what the answer is and we know everything.
Mm-hmm. Yeah. Well, it's a long game. That's the true thing about science. The practicalities do come along, but there's no guarantee that anything you start today you can finish in 1 year, 3 years, 5 years, or
or a lifetime.
Could be beyond your lifetime. Yeah.
Exactly. And as technology improves, we have to, I think, get better at accepting where we've made errors and do it more quickly, because holding on to dogma of something that clearly, as more and more evidence piles up, becomes less and less and less likely, we're really just holding back the train of understanding and of true advancement. I mean, I'll give you the example that I love is when people talk about quantum electrodynamics and Feynman diagrams. There are many people from that time period that have recently passed, and in their passing words, what they said is that quantum Feynman diagrams and quantum electrodynamics was supposed to be this stopgap measure. It doesn't have a good foundation, because you have to normalize all these infinities, and they just don't believe that normalizing infinity isn't actually a real mathematical operation that you can use and say that you have a sound theory.
That's true, but the scary thing is that of course that Feynman diagrams work, right? If you want to predict what's going to get spat out in the Large Hadron Collider, that trick, the renormalization, it works. And so the big question is, why does it work? So clearly it's not right, in a sense that mathematically there are some issues, but also it's not wrong in that it yields the right physical answer. So the question is, where do you take this such that you can put it on a more mathematically rigorous grounds? I think people are still not quite sure.
Well, absolutely, but when you read about quantum electrodynamics, it's taken as this is it. And it is a great, no different than Newton representing gravity. It was perfect until it wasn't. And this is the same thing. It's perfect, but unlike Newton's gravity, we actually have even a little more evidence, because we know that we're normalizing these infinities out, and that you probably shouldn't do that. So there's something about our understanding. It's just about our understanding. We're doing great predictions, but there's something missing in our understanding.
But I think this is actually something that's true in all physical theories, in that there is something in all physical theories, there is some part of it which, some of you know. Okay, so the question is, what's the goal of physics? And I had this discussion yesterday with a student. Is the goal of physics to uncover reality or to find a representation of reality? And of course, there are some of the things that the goal is to find reality. But that's not really what physicists do, right? Leave that to the philosophers to worry about what reality is. What you want is stuff that works. And Newton works, but Newton doesn't give you a mechanism for how gravity works. It just gives you a relationship between masses and distances. And so similarly, Newton itself was not a satisfying answer in itself to explain the universe. And this happens with all theories. Maxwell's equations are great until you ask yourself the question of what's the electromagnetic energy of an electron, and you get infinities again. And you realize that there are places where theories don't work and they have holes in them. but the fact that they do work means that they are useful in the physics toolbox for explaining the universe.
I couldn't agree more. There's the philosophy of it is where I get myself the most interested, because I really do just want to understand how it works. That's what I'm trying to get to, and that is the true basic science. And I think what you're saying is that there's this distribution within physics as a field where you go from more engineering application all the way to true philosopher, where you're just, and maybe this is where theoretical physics comes into play the most, is in this philosophy. But how do we know, like, people can go off on such tangents in the theoretical realms? How do we know that they're even worth pursuing, I guess, is.
So there's a couple of things. Number one is I think you have to be careful about roping philosophers into physics, right? I know that we have philosophers of science, but they tend to stay away from physics departments because they don't get a good reception. So the philosophical aspects are normally outside of the realm of the endeavor of physics. The question about whether or not your theory in front of you is a good theory or not is the same as always. You have to hold it up to nature, and you have to ask, does this represent the universe I see around me? And if it does, then it lives to fight another day. And if it doesn't, then it heads for the dustbin for that realm where it doesn't actually work. So there is a process. Right. And I hate the notion of the scientific method because it doesn't exist as a wash, rinse, repeat kind of thing. But there is a process by which theories have to be compared to nature if they are to be taken as physical theories. And some ideas struggle to get out of the hypothesis stage. Others, once you get to that mathematical description, you compare it to the universe, get ruled out straight away, etc. So it sounds like a terrible war strategy, right? It sounds so sort of like almost aimless about exactly what's going on, but it does sort of heave the front forward, right, with effort.
Well, I can say this, that some of the most interesting things I ever published, I found through complete serendipity. Failed experiment, mistake, added the wrong drug, didn't think at the wrong time. Like, things happen. The neuronal organoids that we grew were a lazy graduate student leaving some culture dishes in the back of an incubator that just happened to be prepared just right, that after a month of leaving them there, he looked at them and the media was still clear. So he looked at them under a microscope, and we could see what looked like a hippocampus growing in the dish. Like, you could just see it in a light, just a plain old light microscope, 20x or something. So complete serendipity. Yet that turned out to be really important. And now, neuronal organoids are one of the hottest topics in biology.
Yeah. No, the serendipity does definitely play a part. I mean, and accidental discoveries happen all the time. I mean, the notion that you run your experiment and you get the answer you expect. It's often the answers you don't expect which are the game changers.
Well, I think that's a great segue into, so clearly I want to talk about the paper that you published, and it is really fascinating. I will say this, it is really well written. Like, I was able to just read it kind of straight through, look at the figures, couple places where I had to look into the method you were using, but really well written. And what you're discussing about measuring time dilation of quasars. And what I'd love for you to do is just to kind of explain just in the simplest, most general terms, what time dilation is and why we would use quasars to look at time dilation.
Okay, so I think maybe the easiest starting place is to go back to Newton. So, Newton was one of the first to lay out mathematical structure of the universe, and you have this stage on which things play out, and that's space. And there's a clock that ticks, and that's time. And to Newton, time was absolute, right? So the same tick occurred all the way across the universe at every single time. Clocks would always remain synchronized. That was all fine until 1905, and Einstein gave us the special theory of relativity. And special theory of relativity essentially comes from exploring electromagnetism. So this was Maxwell's great discovery in the 1800s, was how light is composed of electric and magnetic waves. And what Einstein realized is that if Maxwell's equations were going to work for all observers, then something else has to give. And what has to give is Newton's notion of space and time as essentially these rigid things on which the universe just plays out. They now become these rubbery things. So what Einstein basically said is that in special relativity, the rate at which clocks tick relative to other clocks depend upon their relative motion. So if you have two clocks and they're moving in particular paths, then they no longer remain synchronized. And so there's some famous experiments where people have done this. You take a pair of clocks, you take them on two different journeys, you bring them back together, they show different times because a part of the effect is they had relative motion. So that's the notion of time dilation, is that clocks no longer tick in sync. Things, again, got more complicated in 1915, when Einstein gave us the general theory of relativity, which included gravity. So what that showed is that clocks at different locations in gravitational fields tick at different rates. So gravity influences these clock rates, such that if you're deep down in like on the surface of a planet compared to being up in space near a planet, your clocks tick at different rates. And again, you can do that. You can take a clock and you can take it down to a planetary surface and bring it back up and compare to a clock that was remained behind, and you'll see that they're out of sync. So
they have to adjust the GPS satellite clocks by a few nanoseconds a day, right?
Yes. So because the GPS satellites are in motion at roughly 10 to 20 kilometers per second, and they're at a different location in the gravitational field, you need to take both those effects into account. My understanding was that when the US was developing the GPS system, and of course, GPS was developed not so you could find your way to a party, but so America could plant missiles on Russian silos, right? That's what it was for.
Unfortunately, a lot of great technology has come through the Department of Defense.
Yes, yeah. But my understanding is that the generals, etc., involved were rather skeptical of this need to correct GPS for relativistic effects, right? It was like, this all sounds silly, right? So apparently it was initial tests were, can I turn off the relativistic correction and see what happens? And you see that things wander off. So you need that correction. It's the way that sort of the universe works, is that clocks run at different rates depending upon their locations and their speeds. Now, the other one, which again, this really came to the forefront through the 1920s and by the 1930s, was this realization, of course, that firstly, we live in an expanding universe. So mathematically, this was derived in the early 1920s. Then Hubble's observations at the end of the 1920s showed that space is expanding, right? We live in an expanding universe.
Can I stop you there for just a second? And because I have a question. And this is a very meaningful question to me, because I went through the CMB background papers pretty thoroughly. And I have two issues. One is that there is a paper from this Greek guy, and I'll put the link in the description of the podcast. But he used a radio telescope that was up in a mountain that was far away from any water. And he did the same experiment that they did to get the original CMB data from the Horn telescopes that were actually very close to the water. And his paper went unpublished for 10 years because he tried to get somebody to tell him where his data was in error, because he could not observe anything above background for thermal radiation. So, and then the other problem that I have is the newest data that they took with the satellite that's at the Lagrange point, that is, filled with the cosmic center background that they have to remove to be able to see the CMB background. And the way that they normalize and remove the galactic center, and they change the rules on how they do it every year, and then they take images that are made using different parameters every year and they average them. And just, if I did something like that with a set of neurons, they would throw it, they would immediately throw whatever that work was in the trash. So I want to understand, and maybe you can help me understand, why they would do this, or how it's scientifically legal, because I have a really hard time understanding how you can remove the background from the image in 11 sections that each one has different rules that change. And then how you can make measurements from images that are averaged when these images are altered that are being averaged together. Maybe you don't know this, but I'm curious.
Well, I'm not a personal expert on working with the raw CMB data, but I sort of know the teams that do. And this is not like one teenager in their bedroom coming up with a scheme to work with the data. These are the people that built the instrument and understand the instrument better than anybody else. They also have been involved in previous observations of the galaxy, so they understand the kinds of emission that you get from the Milky Way, and so what kind of model you would need to remove that foreground and just leave the background there. So I said I can't critique the actual.
If you can't, don't, because I'm not trying to put you on the spot. But I'm just asking.
But the question is, does that mean that you wonder if the CMB is actually there? Is that where you're going?
I kind of do, because the thing that really cemented it for me is this radio telescope data that's from, I wish I could remember, I think it's Romania. And that they got 3.5 Kelvin as the background, which it would be kind of what you could predict coming from the ocean that was just a few miles from where the original telescope was mounted and where the data was recorded. And because water is such a huge emitter of microwave radiation. So I have a hard time throwing that out. Now, if someone can convince me to throw it out, I'm happy to. But I want to understand.
So I guess the starting point should be not the discovery of the CMB in the 1960s, but the work that was done in the 1940s. So the work, the notion that the universe started with a hot Big Bang, that started in the 20s and 30s. By the 1940s, there was a realization that the conditions in the early universe would be exceedingly hot. So you get nucleosynthesis, and you get the formation of the first elements. And by basically taking what we know about the history of the universe, the predictions that they got back in the 1940s and into the 1950s was that the universe should be 75% hydrogen, 25% helium, plus there should be leftover radiation from this event. So there was George Gamow was one of the famous ones, but also Joe Silk, who recently got the Nobel Prize, I think it was. So they made these predictions. So these predictions that there should be this leftover radiation came before the detection. So now what they didn't realize is that the CMB had been detected before that. So there was an astronomer working in Canada, and on the top of my head, I think it was McKellar, who was looking at cyanogen molecules in the interstellar clouds. And he found that those molecules had a vibration, and that vibration was as if they were in a heat bath with a temperature of around 3 Kelvin. Right? So that observation was made in the early 1940s, if I remember correctly, right? So it was predicted. And the people at Princeton who had made the prediction were building a telescope to go looking for the cosmic microwave background radiation. And as they were building that telescope, the other guys who had no idea about these predictions were the ones who were over in Homedale, and they were the ones that accidentally they basically went through their electronics and cleaned their telescope, etc., couldn't get rid of the excess background. They phoned Princeton to say, any idea what this is? And they said, basically, we've been scooped because this is what had been predicted. So it's not like, oh, there was a telescope by the water that saw something and then everybody, that's all that people did, right? But then you have to go beyond that, right? So after that, you have dozens of balloon flights. You have then you start to get the satellites. You get COBE in the early 90s, and you go through WMAP and Planck and all this kind of stuff, right? And what you end up with at the end of the day is, let's not worry about the method that they remove the foreground, right? So there's leftover radiation, and it's around 2.75 degrees Kelvin. And the important thing is that radiation is not smooth. That radiation is lumpy, okay? So that radiation has little lumps in it. And the question is, where do those lumps come from? And the only location, if it is leftover radiation, is those lumps are differences in temperature, because when this radiation was released, roughly 370,000 years after the Big Bang, structures had started to form. So some photons had to climb out of deeper potential wells, so they lost energy, etc. So you have this temperature difference. And you get a pattern. You get a particular statistical pattern known as the acoustic peaks. And once they had, with WMAP and then Planck, etc., and even back with COBE, that pattern matches theory to a really high degree. Now, if the cosmic microwave background isn't really there, or if it's an artifact of the reduction technique or something else, then it's really hard to see how everything else holds together, right? The prediction was made, it was found. The prediction was made, it would have this particular pattern, it was found. Yes, as we're not experts in understanding the method that they reduce the data, but I trust those people. I have no reason not to trust them. They understand what they're doing. And
this is where it's like the road to hell is paved with good intentions too, because you could ultimately, trying to put this in the correct context, you could very easily, especially using reams and reams of data, which I have been exposed to, you can very easily manipulate the data because we're pattern seeking beings. Like when I look at a calcium trace of a neuron, I know what I'm looking for, and sometimes I can see things that are not there, if you know what I mean, where it's like, well, in this one neuron you see this, but if you were to average it over 100 neurons, that would disappear and you're not really seeing that, or that is the actual aberrant one. And I could see, when I'm just saying that I can see a way where people are not intentionally trying to manipulate the data, yet in creating the boundary conditions could be even subconsciously manipulating the data that you're getting what you get. Because, and that's, I mean, I'm not saying it very clearly, but I'm just saying that I can still see that happening. I agree with you. There's a lot of coincidence. And that's what keeps me always on the fence, because the theories are matching the data to a certain extent, and that it would be very hard to get that by chance. So I agree with you that it seems like it'd be very hard to get a lot of this stuff by chance.
Okay, so let me just go again a bit deeper. So the patterns that we see in the cosmic microwave background, they're statistical patterns, right? So it's to do with the power spectrum of the fluctuations that we see. And they are measured down to these really small scales, much smaller than the scale of the galaxy. So anything that you're doing to subtract off galaxy emission is not going to put tiny ripples into the rest of your data. And it's not going to put tiny ripples into the rest of your data with the right correlations to give you.
I see what you're saying.
Now, there's another thing, right? So, I'm going to put, I've got my defender of cosmology hat on.
Let's go.
So that, as I mentioned, that ripple that we see in the cosmic microwave background, that's the acoustic peaks. And those peaks are due to the start of structure formation, the start of the formation of galaxies and clusters. Now, the universe has evolved since the cosmic microwave background and has galaxies, etc., scattered around today. And the prediction is that because of a process that I don't want to go into here too much about the interaction between various kinds of matter, that pattern of the acoustic peaks should be written into the distribution of galaxies. Okay, so when we look at how far galaxies are away from each other, they should be preferred distances with like those peaks. And they are, right? Now, again, if you want to say, oh, there's some other magic involved or coincidence involved to make that happen. But I think this is the problem is that it's not one piece here, right? There's a whole number of things which are holding together. And
well, quasars are one of those things, right? Quasars are one of those things.
Yeah, absolutely.
So maybe you could elaborate more on the quasar and why it's a good thing to use in this context.
Okay, so my recent paper then was focused on a particular question, and again that's to do with this expanded space which I mentioned, and we got sidetracked there. This was another one of the predictions.
But we're allowed lots of sidetracks. We can have as many sidetracks as we want, because I'm enjoying this. Maybe in 6 months or a year we'll do it again and see where the universe is at that time.
Absolutely. Okay, so the other prediction that Einstein's relativity gives you is that in an expanded universe, when you look at clocks in the past, they should appear to tick slower. So there's another sort of form of time dilation that we should see. We should look through our telescopes, and the further we look, we should see the universe running in slower and slower motion. Now, this is something that has previously been detected using a class of exploding stars called supernova. So these are massive stars that explode, so they get very bright and then they fade away.
And that
And
can
it took,
kind of give us a standardized candle because they're so bright. We can,
yeah,
okay.
yeah. So they've been useful in charting the expansion of the universe, and they were one of the things that first give us evidence for the presence of dark energy out there in the universe. Now, what was realized is that that brightening and fading time is a time scale. It's a tick of a clock. And so, back over the last 2 decades, people have used supernova and measured the time dilation of their explosions. So looking through the telescopes, the further back the supernova, the slower and slower they appear to explode.
And the further back being measured by redshift, right?
Yes.
Okay.
Yes. But nearby ones are measured by direct measurement, but cosmological ones are measured by redshift. Okay. And you get precisely what you expect from Einstein's equations, that you get this time dilation. Now, the problem is with those supernovas, they're bright, but you can only see them back over roughly half the age of the universe. So the slowest supernova goes at roughly half the speed of the nearest supernova. Now, there's another class of very bright objects, and these are the quasars. So these were discovered in the 1960s. These are supermassive black holes. They have hot material swirling around them at relativistic speeds. So the black holes might weigh, say, a couple of billion times the mass of the sun, lots of material swirling around, all packed into a volume about the size of our solar system. And that can emit as much radiation as 1,000 individual galaxies. So quasars can be extraordinarily bright. And that means that we can see them right across the universe. Some of the most distant objects that we can see are these quasars. And the other interesting thing about quasars is because all of that material is in a small volume, the size of the solar system is tiny compared to the size of the universe, is that quasars vary. So as the material swirls around in the disk, you get turbulence and things popping off. So quasar brightnesses go up and down and up and down and up and down. And we should expect exactly the same signal in their light curves. They should be time dilated in the same way that the supernova are. But because we can see them to much larger distances, we should be able to see them run even slower, way out in the very early universe. They should slow right down. Now, people have looked for this previously in various data sets, and they didn't find the expected signature. And there's a number of reasons for that. And that's number one is that supernova, as you said, you can make them into a standard candle, but quasars are more diverse than dogs, right? You go from big dogs to small dogs. Quasars can vary by factors of 1,000 in brightness. So the variability of one quasar might not be like the variability of another one. And there's another effect, which is, as we're looking out into the universe, as you mentioned, light gets redshifted. So if I'm sitting here on the Earth and I'm detecting light and my camera is sensitive to red light, the wavelength that light was emitted at gets shorter and shorter as we observe to higher and higher redshift. So the nearby quasars, it might be green light. And the most distant quasars, it might be coming from an ultraviolet region. So again, because the source of emission is different, you might expect the variability to be different. So in reality, when people looked at quasars, I think all their signals were mixed up and they couldn't pick out a standard tick. Now, what happened last year, there was a group in the US and they published a sample of 190 quasars that had been discovered with the Sloan Digital Sky Survey, which is a telescope that was running since the 1990s, right? Just surveyed the sky from Apache Point in New Mexico. Surveyed the sky, surveyed the sky, surveyed the sky, and they focused on one patch called Stripe 82. And in that patch, they identified quasars. So they found the quasars and they made sure they were quasars and said, right, look, we've got this sample. And they've become sort of like a test bed, right? They're well-known quasars.
And they've been recorded for like, what, 10, 15 years?
Well, now it's over 20 years that people have been going back and looking at these quasars and collecting their light. So they managed to collect the light from 190 quasars over 20 years. Now, their sampling is not even, and they've used different instruments, but they have pretty good light curves. And what was also realized only in the last 10 years or so is we started to really understand the statistical properties of quasar variability, right? And what I mean by that is that their variability looks a lot more like the stock market than it does like a simple sine curve, right? It has ups and downs on various scales, etc. And you can't predict exactly what the light curve is going to do next, but you can predict what's going to happen to it on a longer sort of time scale. It will go back to some sort of average and this kind of thing.
So you could actually use like a machine learning type algorithm on this data to create a model that then should pretty accurately predict what variation these quasars are going to go through.
So this is what this group did: is they used a thing called a damped random walk. So random walk, scatters up and down, but it has a time scale in there. And they fit the light curves using Gaussian processes, which is an AI kind of thing for filling in the gaps in your data. And but the important thing is that statistical description, the damped random walk, contains a time scale. So once they published that, I said to myself, maybe I could use this as the tick for each of the quasars. Now, we still have the problem that all the quasars are still mixed up, right? Some are bright, some are faint. But now, because we've got this really well-defined sample, I could start to group quasars together. So I could get like a group of the brightest quasars, which are observed in their rest frame ultraviolet. So, that's coming from the material closest to the black hole. Or the fainter quasars, which are observed, say, in green light. So that variability comes from somewhere else. So in each sort of sample, I got like quasars. And so in there are quasars which I think are similar. And I've got their time scales. And the only thing that could give me a difference in their time scales is the effect of the cosmic expansion. So that's what I looked for in each one. Is I said, all right, they should be the same, except for the effect of cosmic expansion. What would the effect of cosmic expansion be? And that's what I went through. And so I did a bunch of tests on, are they the same? Are they different? And if they are different, how are they different? And what we found is that the best hypothesis is that the difference is explained by the expectation that we get from the picture that space is expanding.
Right. I mean, it was beautifully laid out in your paper, your hypotheses 1, 2, 3, 4. And my old mentor, Saul Snyder, would be lauding you for the way you wrote your results, because that's how he writes results. Very precise, very clear, to the point. So
okay, thanks.
So you use different devices. Are each of these all in this? You're collecting just in the visible light spectra?
So each quasar was observed in 3 bands. So there's a green, a red, and an infrared. So in each one, there are 3 light curves corresponding to each of those bands.
And then how similar their output was in each of those bands is what helped you to classify them into your groups.
That's right. So one of the things you can do is you can work out what the total output of the quasar is. So it's total luminosity. And then we can use the redshifting to work out where the emission, at what wavelength the radiation was emitted at before it gets stretched and arrived at our telescope. So that allowed us to characterize similar objects into the same kind of bins.
So being as there's so much cosmic dust between us and all of these things, and that in the infrared, the dust, depending whether it's near or far, the dust will either appear or not appear, and then it will really be visible in the visible light. And then not so visible again in the ultraviolet, the stronger light. How did you have to deal with that? Did that come into play as you're making your measurements?
No, so look, again, the measurements were made by the team in the US, and
Right,
they
right.
take that into account. So the thing is that we understand the distribution of dust in the Milky Way. So the biggest influence of dust, other than in objects themselves, which are really dusty, is the Milky Way galaxy. And people have spent decades mapping the sky in infrared light, and that allows you to characterize the properties of the dust over the entire sky. So you can get dust maps for any region, especially that region where Sloan looked. So you can do a correction. You can correct for the influence of dust.
Okay, so yeah, so that's just actually a fairly simple background correction, because you have a solid piece of data that's been collected over years where you know in that region what all of those effects are.
Yeah.
So what was the most surprising thing that you got from your work? Like, what was the thing that you were just like, wow?
Well, so I guess I was surprised not to be surprised at some level, in the sense that no, this is like one of those fundamental measures of what's going on in our universe. So the thing, it doesn't care about the presence of dark matter or dark energy or those other things which you worry about. It tells you, do we live in a relativistic universe described by expanding space? And the answer is yes. So that's what it comes back as. And it comes back as that quite strongly. So that was a very satisfying result. If it didn't come back as that, we would have to scratch our heads a lot about what is happening to quasars on top of the cosmic expansion. That means that the cosmic expansion signature is distorted or lost somehow. But it didn't happen that way. It comes back that they said the strongest thing in there is the expected cosmic expansion.
Yeah, so I think, just to make it clear for anybody listening to this, your paper really, it is a statistical analysis that is, the statistics say that the hypothesis that the universe is expanding is the most likely hypothesis, and it's within a pretty narrow margin.
Yeah.
This is the, like, if you were to boil it down to one sentence, that's what you could say.
Yes.
So but it doesn't necessarily mean that that's what's going on. However, if you were to try and tease what I just said apart, let me do this. Can I just ask you a couple of questions that I would love to, because it's all related. Because, like, one of the things that I'm seeing now, which also plays into what you're doing, is, we're seeing all of these lensing effects, which is also due to gravity, which is also due to the redshifting of the light. I keep reading these papers where, there's a lensing effect that's caused by two invisible white dwarf star binaries that, like, and even what you said, like not getting into dark matter, dark energy, there are these things that you see where you read it and you're like, what are the chances in your experiment, and you have a very clear result, but it's also, what are the chances that a binary red dwarf star constellation is right in front of this in the perfect manner that you can get this type of lensing effect? It's like it becomes hard to digest, because it seems like anytime something goes against the standard model, there's something new invented that allows for that. Like, I'm seeing now dark atoms, and there was a new paper that just came out about dark atoms, and it's starting to blow my mind, because it's like, your work, I read it, and it seems very clear it is a statistical model that's, vetted, that has, I mean, when you go through your distributions, how you're doing it, you're fairly characterizing the way you've binned the quasars, and, you've applied a mathematical model to it that can predict. And so there's this great correlation. Yet there's things like I just described to you, and they have to invent things like modulators to understand how they're seeing the effects they're seeing. And I just am like, where do you fall in all of that, where these things come out that are not easily explained and people create a new caveat to include them in the standard model?
Well, let's go back. First, I can go back to the lensing one. I mean, lensing is an area that I did my PhD in, actually, so
Oh,
it's something I
cool.
know about. So the thing that you said about essentially what's the cross section due to lensing, right? These are things that were calculated actually long before many of the lensing experiments were done. So like this notion of, what's the chances of a star passing in front of another star and giving you a particular lensing event? It's roughly 1 in a million. And that's what they see. They look at a million stars and one of them is doing something interesting at any particular time. So the statistics work out. I don't think there's any magic or sort of manipulation that's going on there. You might fine tune the numbers somewhat, but the order is of 1 in a million. For quasars, what's the chances of quasars being gravitationally lensed? It's roughly 1 in 1,000. And when we look at them, that's what we see. It's roughly 1 in 1,000 that we see are being lensed. So those statistics come from relatively straightforward calculations on the number and mass of galaxies and their distribution through the universe. Now, well, sorry.
No, I was going to say, well, will you look at a picture with me?
Yeah.
So let me share my screen. So this one, I think, is really interesting. And what galaxy is this? I gotta get my glasses on to see. This is HEK 1920 from the catalog. So this is one that where the paper that was published on it says that this is showing this galaxy or quasar lensed 12 times. This is what they're reporting. And here we can see the clear lensing event. But there's also things like I can see a lensing event here. Let's draw some circles. See if we can kind of. So like clearly you can see this one. It's not perfectly circular, but it's pretty close. But then you have another one here, and I mean, I could almost even argue that you have another one. Well, depends. See, it kind of depends on how you do it. So it's like I could see 3 different lensing events in this if it is lensing, but then I want to blow this up because this is the microscopist in me, because that was what I did for so long. Blow this up even more. Back one. So if we just take this little space right here and you say, if this is a repeating pattern and it's lensed, gravitationally lensed, and it's a single lens, it should be flipped and inverted, correct?
It can be, yes. Doesn't
'Cause-
have to be.
well, because I mean, if it's lensed, I mean, well, if it can't be a mirror reflection only if it's lensed.
No, it can be.
How,
So this is what the problem is here. Now, so number one, you said, if this is a single lens, but this isn't a single lens. This is a cluster of galaxies, right? So the lens itself, the thing doing the lensing is complicated. So it's not like a simple glass lens. It's more like the crinkly glass you see in a bathroom window. Okay, so you can see multiple images of the same object. Now, exactly what their structure looks like depends upon what the effect is of all of those other little galaxies in there. So if you look at the break between those two, you can see that there's a little spiral galaxy in between, and that spiral galaxy is influencing the lensing potential. It's changing the potential. So you get lots of wiggles in there, which give you lots of bits and pieces.
I see what you're saying now. So you're saying that it is not one lens. It could be, I mean, just looking at this image, it could be, well, what's in plane, what's close enough to it, it could still be tens of lenses.
There tens of masses in there, if not hundreds.
If not hundreds. Because we could also have things that are in the far infrared that are very massive that we're just not seeing, or in some spectra that we're not observing.
Yeah.
Okay. All right. I really appreciate that, because I'm going to take another look at this and I'm going to go back to it. Because I was under the impression that when you have this type of an event, this type of a lensing event, that there's a single lens. That's
No.
the combination of all of the gravitational influences, and that we're catching it at one point. And what you're saying is, no, they aren't all working together to create the lens. Each individual point of gravity is a lens, and that is what's causing this copycat effect.
Yeah.
In the stretching.
Yeah.
Okay. Well, then we can come back to that at another time. I noticed when you talked about dark energy and dark matter, you were like, we don't have to get into that. Do you have trepidations at all about dark energy or dark matter? Are you of the mindset that these are moving towards settled science, or do you still believe that this could be that we're misinterpreting something, that this dark energy and dark matter that we're attributing may still not be fictional?
Well, firstly, there's no such thing as settled science. I mean, I hate that phrase. No science is settled, because there's always more work to do. My bet is that dark matter is something physical, in the sense that it is a material object. If I was going to put a bet on that, would be the odds that I would go for. The idea that it's actually due to us not understanding gravity. None of those theories are really compelling that have been put forward. They all fall down badly in places. Dark energy, again, I don't think we're being fooled. I think that the observations that the universe is accelerating, I think they are, again, unless we've missed something else in Einstein's equations, I think they're reasonably compelling at the moment. But what the source of dark energy is, I don't know. I wouldn't bet much on any particular idea for that at the moment.
Okay. I mean, just because we've been having a very nice conversation, and I want to end it on a really positive note. What kind of advice would you give to young people that were thinking about going into science, going into physics, in particular with the number of graduate student slots for physicists falling dramatically in the last few years, mostly because of reductions in governmental funding.
Yeah, well, I for a graduate student, I would just say, firstly, enjoy it. I mean, there's
But you have to get into it. Like, that's my point.
yeah,
Like, the number of positions is dropping rapidly
that,
because people can't afford the graduate students. And so even if you wanted to do it right now, you have to fight even harder just to get a seat.
well, that's true, but it's not globally true. So, like in Australia, we have a government-funded scholarship scheme for students. So we still have very healthy numbers of students. The problem that we have is the next step is what happens after you get your PhD or had your first postdoc, right? And so for people, so firstly, I guess I don't know the US system that well. The I think the typical graduate advisor is looking for somebody who can demonstrate they've got well-rounded skills. Right? The problem is that most people going into a graduate program don't know what a graduate program actually involves. They don't know. They often don't realize they need to program. They often don't realize they need statistics. They often don't realize they need to talk in public. They often don't realize they've got to write things down. And so demonstrating those basic research skills, I think, are a key tool. But then in choosing what it is you want to do, you really need to, firstly, don't chase wagons. Please don't chase wagons. Right? So if somebody tells you this is the hot topic, take it with a pinch of salt. Go into a field that you are going to enjoy, because you want to wake up in the morning and say, oh, I'm keen to answer that question, not, oh God, not another few hours in the lab, right? So I think it is choosing that path that is going to keep you interested is the important one.
What made you know that you wanted to be studying the stars? Like, how do you find that?
Well, I've had an interest in physics and the universe from a relatively young age. I don't come from an academic family, but I had that kind of interest. When I was a undergraduate, I wanted to be a particle physicist, right? And so I had sort of drank the Kool-Aid, the Feynman Kool-Aid, all that kind of stuff. But then I did a summer school at CERN, and I sat in a room of the L3 experiment with 1,000 other people listening to Sam Ting, the Nobel Prize winner who was running the experiment. And I looked around the room and said, how am I going to make an impact if I go down this path? So I sort of decided there that even though I liked particle physics, I thought I could do more in astro. And so I sort of leaned back the other way then.
So it was really somewhat of clearly a passion for it, but also somewhat, what's the word I'm looking for? It is still only 7 a.m. here.
Yeah. Well, I think again, the advice to a prospective grad student is that if you have research opportunities as an undergraduate, then be diverse, right? You go and see what the photonics group does. Go and see what the astronomers do. Go and talk to the person who works on neurodynamics or whatever it is, right? And just see what people do and see what sparks your imagination. Well, you don't know until you know.
I mean, this was always considered, by my superiors in academia, it was always my quote unquote problem, because I went where the question took me. And if, the things that I was trying to study were global questions. And if you start asking global questions, you start having to be a globalist, where if I want to truly answer that question, I have to now get into statistical models. And if I truly want to answer that question, well, I have to get into information theory. And if I truly want to answer that question, I even need to start understanding particle physics. This is the road that you can get led down. And I think a lot of times in academia, they keep telling you, oh, you need to be focused and you need to be focused. And they don't allow younger scientists to be so broad because now you're not focused. And it's like, but you're the most productive also in your 20s and 30s. The data, the scientific papers have been published in PNAS. Like, we are the most productive before 40 years old. That's when we do all the work. And I feel like that's where you should be supporting young people to do exactly what you said. And really the focusing point should be in your 40s. When you have this broad background, when you can take information that you get from a particle accelerator and apply it to the universe. That's true knowledge and understanding. And the more scientists we have that can bridge those gaps, the better our science is going to be. And I feel like this compartmentalization that people have gone through in the scientific disciplines has actually been really detrimental, in my opinion.
The most interesting people I always meet are the ones that have done a lot of different things and can talk broadly on lots of topics.
And you seem to have done that as well. It's like very easy to communicate with. I hope that when people watch this, that they recognize also that, you know, I still have opinions that like we're not satisfied. Like, we would need to talk for 20 hours to even start getting to the bottom of where my mind is living. However, we can have a really collegiate and congenial conversation and have some differing viewpoints and not be polarized, not be throwing knives. And I think that this is really important too, because I don't know if you have been, but I've been to many a scientific conference where people just start throwing knives at one another. It's no longer about who's really right or wrong. It's, can I catch you in something and make you look bad? And I wish that as a society of scientists, we would start taking this type of an approach where, no, you're allowed to push back. You're allowed to have a different opinion, and I'm not harming, and you're not harming one another by having these things. It's still, in the end, you, the observer watching this, should be making your own informed decisions based on the information that you get and take in. And if you haven't done a lot of work to take in a lot of information on a topic, you should learn to be very reserved before making judgments, because otherwise, a lot of times you're going to be on the wrong side of the coin.
I agree. I'm not a big fan of scientific fighting. I don't think it achieves very much.
I don't think it does either. I think the only thing it achieves is creating a public sentiment that we're just a bunch of, for lack of a better term, whiny bitches fighting with one another. And it does appear that way from the outside sometimes. And it's hard to take people like that seriously. It is, because we see it in politics all the time. And what do we think? Well, I have to say, Geriant, it was a real pleasure speaking with you. I really would love to do this again at some later point. And maybe as keep in touch, and I'll ask you some questions here or there. But really appreciate your time, and I hope that things go well on the Down Under for you.
Thank you. And look, happy to chat again in the future. It's just ping me a message and we'll make a plan.
Fantastic. It was a real pleasure, and I'll talk to you soon.
Okay.
All right.
Bye.